Oh, may I ask a quick question before we begin?
Yes, hello. You can ask a question. Go ahead.
What's the difference? Like, what's the wording in a question when they ask for WD or just WN?
Okay, thank you for your question. Basically, they are meaningful in force vibration. When the system is excited by initial displacement or initial velocity and is in the natural vibration, the system will always vibrate in its own single degree of freedom, natural frequency, or multiplication of summation of amplitude of natural frequency. But when it comes to force vibration, and the system will vibrate with the external, basically, vibration. And for the system that there is a damping. When there is a damping, in order to be more exact, in order to find the natural frequency, we could say damped natural frequency. Zeta has very, very small infinitesimal effect on the natural frequency, but in most of the time, the effect is very, very small. And if you're not asked to do that, you can easily find the natural frequency without basically the considering the zeta. So omega d is a stand for damped natural frequency, which is equal to omega n multiplied by s square root of 1 minus zeta squared. On the other hand, natural frequency is just properties of the system. And let me just turn on the, today we are gonna do some just review for chapter 2 and 3. We are not continue the chapter 5 because you're gonna have an exam midterm, I think, and your professor asked me to do additional problem in chapter 2 and 3. I have provided some problem, and we will go for solving some of them. Okay. If you have any specific problem in the chapter, or I can solve it for you, or we could go over it together. If you have particular question for any problem in chapter 2, 3, just let me know. So, so I'm waiting for, I'm trying to connect to the, basically, okay. Okay.
So let me share the screen and we will go for sharing. Okay. So just let me know if you hear my voice clearly. And
yes, that's fine.
So Tommy, you asked me for damp. Basically, omega D is omega n 1 minus theta squared. So if it is written, there is a damping in our system, and you're asked for damp natural frequency omega D, and you have to basically calculate by a multiplication of omega n by s squared of 1 minus zeta squared. And so since there is a damping, the natural frequency will a little bit affected by, because zeta in our practical application, if you see something in real is vibrating, of course the damping should be around 10%, 0.1. Otherwise you cannot see the vibration. If system has zeta greater than 0.3, 0.4, it will be definitely a stop after 2 or 3 cycles. So if you in the nature, if you see something is vibrating, you have to understand that the damping is about 10%. So it's about 0.1. So if you multiply it, if you score, for example, if omega is 10 multiply 1 minus 0.1 plus 0.1, it would be more or less the same, around 10. So it doesn't basically affect that much the value of natural frequency. But however, in order to have the value of damp natural frequency, you have to calculate the damp natural frequency through multiplication of omega n by 1 minus zeta squared. However, you have to be very, very careful in solving force vibration. You cannot say that for the sake of simplicity, in the final answer, I want to say, for example, I cannot recall the solution for the, in the final answer, you cannot say this is, I can say this is omega n, because it is a, you are not supposed to do this assumption. You have to keep it like this if there is damping in the system. So you cannot simplify the solution because the answer, because tau d is 2 pi over omega d, and after some cycle, the error will be accumulate basically. So you cannot ignore the omega d in the response. And so I have prepared some problem. Let's go for chapter 2 and then we'll go for chapter 3.
Thank you for the answer.
Pardon?
I said thank you for the answer.
You're welcome. You're welcome. So omega d system is critical damp. System is under, okay. 2.36 point 36. So 2.36. I have gone through chapter 2 and 3. I found some problem. If you have a specific problem, just let me know. In chapter 2 or 3, we can go over it. 2.36, it says a vibrating system is started under the following initial condition. So x is 0 and x dot is v naught. So determine the equation of motion when, so there is a system, you can basically plot you can model the system by a spring damper like this, M, K, and C, and determine the equation of motion. So we are heading toward finding equation of motion for 3 cases. Case 1 is when zeta is 2, b zeta is half, and zeta is 1. Zeta is 1. So plot non-dimensional curves for the 3 cases with omega nt as abscisic and omega n as a x omega n over v naught as an ordinate. So I want to remind you that based on the value of zeta, we have different system, and for the case A, in the exam, normally you have a formula sheet. You have to choose, there are a bunch of formula. You have to understand which one is related to overdamp, underdamp, critical. You have to find the solution for free vibration or forced vibration. You have to at least go over it before exam, and you have to be familiar with the solution and pick the right formula for your question. And for case 1, zeta is 2 is basically overdamp system. For case A, overdamp system. So for the overdamp, basically, response of a x of t is basically can be written as a multiply e to the minus zeta plus zeta squared minus 1 omega n t plus e to the minus zeta minus zeta squared minus 1 omega n basically t. So which is a basically response for a free vibration due to initial condition. This is a response, and since basically the zeta is greater than 1, the system will be basically overdamp and will not vibrate for a case of zeta greater than 0 and lower than 1. And in order to find the response, all you have to do is just finding the coefficient A and B. As soon as you obtain coefficient A and B, you will be able to represent and plot the response base, and you will be able to have the response of the system at any time, at any specific time. So we have initial condition available as x of t at time 0 is given as 0, and also the velocity at time 0 is given as v naught. Okay, so if I plug in here t as a 0, therefore a and we have a general solution for a general solution, basically general solution to the question. If you solve it for general solution, general case, when x at time 0 is x0 and x dot velocity at time 0 is v naught or x dot 0, there is a formula for A and B. Basically, A is x dot at time 0 plus zeta plus zeta squared 1 minus 1 omega n x of 0 over 2 omega n zeta squared minus 1. Similarly, B would be, or you could do it by yourself. You can manually obtain this equation. You have to just plug in the value. You are not supposed to memorize this formula. All you have to do is just pick in this equation, the response. It's like a system like this, and you can easily find the A and B. You are not supposed to have this formula A for B just for your fair information. I'm trying to give you, but you have to be very careful. Multiply omega n x of 0 over 2 omega n zeta squared minus 1. So if I insert, substitute the initial condition, therefore A would be V naught over 2m, 2 omega n, 2 omega n, 2 omega n a square of 3 and basically three to n. So A is three. So B is minus V naught over 2 omega n square root of 3, and you have A and B, and you can develop the response and you can plot it. If it is required, you can easily plot x of t V naught e to the minus 0.268 omega n t minus V naught over 6 omega n multiply e to the minus 3, 7, 3, 2 omega n t. And this is the response for basically, you can factor out if you want, but this is okay. And you can plot the system. So for part B, zeta is half. You have to be able to, you are supposed to know what is the right answer for the response under damp. Under damp case, zeta is greater than zeta and lower than 1. The response of the free vibration is x of t. You have to pick up the correct answer, the correct formula in the answer sheet, or you have to derive it. So e to the minus zeta omega n t multiplied by initial velocity plus zeta omega n multiplied by initial velocity over omega d damped natural frequency, omega d sine of omega d t plus x naught initial displacement multiplied by cosine omega dt. So this is the general solution for free vibration when the damping in our system is between 0 and 1, which is called undamped case. Underdamp system. So all you have to do is just plug in initial velocity and initial condition. So here I made a mistake here. This is, so if I plug in initial condition to the response, therefore the solution would be x of t V naught omega n e to the minus half zeta omega n t over omega d. Omega d you can calculate as omega n squared of 1 minus zeta squared. Basically omega 2 point. So okay, if you calculate, if you plug in zeta as 0.5, this would be 0.865 omega n. So plug in here 0.865 sine of 0.865 omega n t. So the response would be something like x of t. So initial, at time 0, there is no any displacement. And so since it is not forced vibration, it will be definitely, the response would be 0 as soon as time increases. So here, if time becomes infinity, the response becomes 0 because it's free vibration. So the velocity here, the slope is initial velocity, and this will be the response of the system. There is a formula for natural log that relates this amplitude x1, x2, x3. We solve in the class, in the tutorial. It's very important with what decay, which rate basically this is going to, the rate of system will be decreased. So you have to calculate the natural log, logarithmic decrement, and relate x1, x2, and x3 together. We already solved in the tutorials. These are very important. Generally, you will be asked in the meter. You have to be able to read. In some cases, you will be given this graph. At first, you have to understand what is type of system. It is either overdamp, underdamp, or critical case. You have to be able, you have to go over the graph in the book. You have to relate what is a critical case. You have to read, you have to understand the phase graph, the graph for the phase. And in some cases it's given to you, you have to calculate natural log. So you have x1, x2, for example, x1 over x2, if I correct, it is e to the minus delta t or something like that, e to the minus delta. So you have to be able to read the graph. You have to guess what is this response of this type of the system. This is one of the questions in the previous meter. You have to find logarithmic decrement, type of the system, overdamp, underdamp, critical damping. So for the part C, suppose zeta is 1. So what is the response? For the critical damp case, the response of the system x of t basically is just so you have to just plug in as the previous question, just plug in zeta as 1, there would be the response. So it's very simple. The response would be x at time 0 plus initial velocity plus omega n initial displacement multiplied by t e to the minus omega n t. Therefore, the response of the system x of t v naught t e to the minus omega n t. This is the response of the system. If you want to plot, so you can easily make it dimensionless omega n t and x omega n v naught, x omega n v naught. So x over v naught, there would be t e to the minus omega n t. So you can multiply, okay, we can multiply the two side by an omega n. Therefore, you will have omega n x v naught as omega n. Okay, I see. Omega n t e to the minus omega n t. So you can consider it omega t as alpha. So alpha e to the minus alpha. So you have to just plot you can just put some number and plot the graph. It's so easy. So alpha e to the minus alpha at time 0, you have the response. You have the response. You can give it t0, t1, t10 and calculate the response. And the overdamp case. So basically the response would be zeta. So if I couldn't the response for the overdamp, you just have to plot critically damped. So depend on the initial velocity. So this is a general solution. For example, if x naught is not 0, and it depends on the initial velocity. If initial velocity is 0, so the slope at time t is. So here, for example, there is a positive initial velocity. The slope is 0, v naught is 0, and the negative initial velocity. So you can easily plot it by just giving some numbers. So we are done with problem 2.36. 3 different cases, the response of the system. And deriving equation of motion is very important. Let me find a problem for deriving equation of motion. Generally, you will be asked one question in the exam to find the equation of motion, either using Newton law or effective mass or effective stiffness. For example, 2.32 or 2.41. So for example, 2.41 equation of motion. So there is a system here. Stiffness. There's a beam basically, and there is a mass at the end, which is attached from upside to the stiffness and from downside to the damper. You are supposed to find initial condition. This is basically A. This is L. This is going to rotate around this point O. As I told you, for the rotational system, it is better to take advantage of, particularly for single degree of freedom system, you are supposed to take advantage of Euler formula. So summation of momentum around point O is mass moment of inertia around point O multiplied by theta double dot. So it's better to consider a positive direction. So let me consider a counterclockwise as my positive direction. If you consider counterclockwise as your positive direction, you have to, it's better, for the sake of simplicity, it's better to rotate the system slightly in the direction of positive direction that we consider. So, and also, as I told you in the previous session, when in the system, the amount of mass will change the static equilibrium position, you can ignore the effect of mg. So here, if I had a greater mass, the system will be stationary, will become a station at a lower case. So here we could remove the effect of mg because in the static equilibrium position, the contribution of mg in the rotational, the system around point O will be cancelled out by k delta static and c x dot kx. So all you have to do is just say, I assume this is the static equilibrium position right now. This is my assumption. You can write that the mg term will be cancelled out by k and damper. So I solved in the class for a linear case. I proved that you could easily cancel out and ignore the mg. So I assume this is my static equilibrium position, and from this position, I rotate the system toward the positive direction that I assume. As soon as I rotate the system slightly, so let me plot it again, the damper and the stiffness will be oppose the motion. So the stiffness will oppose the motion, and also the damper also. So it would be k x dot, and damper force would be c x dot, k x and c x dot. So this is theta. This is basically theta, and this length is in the previous session we understand that how to relate basically this x and a and theta. X is nothing but a multiplied by theta, right? So we could assume like this. So this is basically your free body diagram. It is better to plot it in the exam. So at this point, you can easily apply Euler formula. Summation of momentum around point O is J naught theta double dot. So momentum is force multiplied by the arm. So I'll have a kx force. So this kx will create a basically positive momentum around point O, right? So all you have to do is just consider a negative, because multiplication of kx at the arm will create a clockwise momentum. That's why you have to consider a negative for the momentum. So kx, this is the force multiplied by arm. This is a momentum due to the contribution of the spring. Again, for the damper also will create force and also thereby creating momentum. Cx dot multiplied by the arm will create similarly clockwise momentum. So clockwise is the opposite of the positive direction we assume. So you have to say minus Cx dot multiplied by A. So force arm, this would be momentum, right? So this is going to be equal J naught theta double dot. as I told you in the first two sessions, you have to either have equation of motion in terms of x or in terms of theta. All you have to do is just changing all the parameter and describe all the parameter in terms of theta, or you have to describe all the parameter in terms of x. So let me, since the system is rotational, let me relate x to the rotational movement, and easily you can say x is a theta, and just plug in here. Therefore, simply you will reach this point, minus k a theta a minus c a theta dot a j naught theta double dot. So when you have a mass like m, which is rotated around point O, j naught is ml squared, mass moment of inertia. So I can easily plug in here ml squared theta double dot. By further simplification of this equation, I'll have minus ka squared theta minus ca squared theta dot equal to ml squared theta double dot. Therefore, I'll have ml squared theta double dot plus k c a squared theta dot and plus k a squared theta is equal to 0. For the sake of simplicity, you can divide both sides of the equation by ml squared. Therefore, the final equation of motion simply can be written as theta double dot plus cm a over l squared plus k over m a over l squared theta equal to 0. So you can easily calculate the natural frequency. When the coefficient of theta double dot is 1, this would be natural frequency, omega n squared. Therefore, omega n would be a over l squared of k over m. This is how you obtain the equation of motion and then natural frequency if you want to solve it. Basically, 2.41. 2.41, set up the equation of motion for the system. We already set up the equation of motion. Determine the expression for critical damping coefficient. So determine the expression for critical damping coefficient. Critical damping and natural frequency of damp oscillation, omega d. This is omega n, and omega d can be simply obtained omega n 1 minus theta squared. So critical damping coefficient C critical is 2m omega n. So 2m omega n obtained here a over l squared of k over m. This is critical damping. This is a damp natural frequency. So we obtain omega n. All you have to do is just plug in omega n here and just multiply by zeta. We don't have a specific zeta. Keep it as an unknown value, as a parameter. So basically, critical damping, we are done. And zeta can be related to C. Okay, C here. So we are done with equation of motion. Basically here, if I want to recap, we are done with equation of motion here. Equation of motion, we are done. And we are done with critical damping here, critical damping. We are done with this part. And for damp natural frequency, omega n we obtain. So for the zeta, we know that damping ratio, right? Damping ratio is C over C critical. So C over 2m omega n. So you have zeta like this, just plug in here, and you have the omega. Therefore, if I plug in both at the end, the zeta would be Ca over L square root of K over M. Just plug in omega n as what we obtain. So another, so we are done with basically this question. So I'm trying to give you a hint for how to relate basically omega n squared. Okay, so here, as I told you, the equation of motion can be written as this general form. So you can detect basically, this is the general form of equation motion. You can just hand in formula. So theta double dot plus 2 zeta omega n theta dot plus omega n squared theta equal to 0. This is a general equation of motion when there is a damping. So you have the equation of motion by equaling the coefficient for each term. For theta double dot, theta dot and theta, you can easily or simply in a shorter time you can relate omega n zeta to the C and K. If you don't have the formula, if you don't want to memorize, there is no any problem. You can easily just go for the available formula. You can just take a look at the equation here. When the theta double dot coefficient is 1, you can simply say the coefficient of theta or x is omega n squared, and there is a formula for omega d, and for the critical damping, you can easily find them without having any specific, without memorizing different or complex formula. So we are done with this question basically. And if you have any specific question, just shoot me. Otherwise, I like to solve a question from chapter 3 for a vibration measurement. It's very important, vibration pickup. It's very, very important because every semester I notice there is a problem from this part. So let me just go. These are very important questions. Equation of motion. You will be asked natural log we solved in the class, and vibration measurement, seismometer, estimating displacement, or accelerometer, estimating the acceleration of the base. So by considering some error, you have to relate and find the range of omega that the device can estimate within a specific error. You have to identify that range. It's very important. And vibration isolation, we already solved. Transmissibility and vibration isolation, these are very important. So let me solve 3.42 for you in order to make sure we already familiar with vibration pickup. If we have time, we could come back for the chapter 2 and solve other questions. So 3.42. These are very important questions. So a commercial type vibration pickup. Commercial type vibration pickup is generally referred to seismometer. It is not accelerometer, basically. It is a seismometer. So a commercial type vibration pickup, or it means amplitude pickup, measuring the amplitude, estimating the amplitude. Each device has a specific natural frequency. So we discussed in the last session that the natural frequency of seismometer is relatively small compared to natural frequency of accelerometer, which should be very high in order to be very exact. So omega n of the device is 4.75 cycle per second, which is stand for hertz, right? So this is the natural frequency of the device. The device has a damping factor, it means zeta. The damping factor of the device is directly given as 0.65. We are supposed to find the lowest frequency that can be measured within 1% error and 2% error. I can easily remember in the question in the previous semester, you have to, I will describe in detail. So what is the lowest frequency, omega n or f, lowest frequency that can be measured by this device can be measured within A, 1% error, and B, 2% error. So as we discussed in detail in the last session, we have gone through the property of this vibration pickup, and simply the vibration pickup try to estimate the amplitude of their input oscillation, try to guess as Z as a measured value, the output number that you could read from the device over the real displacement, the real excitation amplitude. We want to basically estimate that. That's why we use a seismometer or vibration pickup in some factories or in the building in order to see what is the amplitude from the basically earthquake, from the wind. So we need to calculate the amplitude. In some cases, you need to, for example, for designing seat suspension, for designing seat suspension for automobile, you have to put some accelerometer in different part of the body in head, and you have to calculate the output acceleration. For example, if you want to assess how much vibration will be transferred to the hands of workers which are dealing with using drills. So you put some acceleration in their hands and you can measure the acceleration transmitted, the amplitude transmitted. There is a basically guideline standard and there is a specific range of acceleration and displacement that people can tolerate daily based on time, 8 hours per day. So you need to know them for designing and developing this standard and designing suspension system and everything. So these are very important. So size parameter z over y, z is measured value, estimated value, y is the correct amplitude. So I prove it last session, which is equal to r squared. R is natural frequency ratio, a square root of basically 1 minus r squared, s squared plus 2 zeta r s squared. So this is the formula. So it's very easy. This is basically measured value over real value or correct value. So 1% error. 1% error could be z over 1.01 and or 0.99. So mathematically point of view, if you don't know how, I told you in the previous, if you go through the response of the system, it depends of if you have the response for some zeta, z greater than y, and for some zeta, z is lower than y. I plotted, and if you don't have any plot and if you don't have any vision for the graph, you can just take advantage of mathematical equation. So you can go for these two cases and calculate the R. So suppose you do, here basically zeta is given 0.66, 0.65, and suppose we don't have time to plot the graph, we don't know exactly z greater than y or y greater than z. All you have to do is just try to find R for two cases. This is very important. So in the exam, right, case 1, I want to consider and assume z over 1 is equal to 1.01, and I will consider another assumption 0.99. So because we don't know exactly z greater than y or y greater than z. So because this ratio is depend on the zeta and frequency ratio. So mathematically point of view, we will go first for, so in summary, so for each case, you will go for finding R, R1 and R2. This is basically omega s squared over omega n s squared and omega s squared, omega n s squared. So basically, these R should be positive. The case that gives you both negative. So in this case, for example, maybe R1 is negative, okay? And R2 is positive. And suppose for this case, R1 prime is, for example, positive, R2 prime is negative. So here it gives you some range, and here will give you some range. How? I will tell you how. For this case, so let me, I just detach this part together. So take a look at here, z over 1 here. Z over 1 for the first case, z over 1 we wrote as 1 point. So it means, so you can translate this equation, z greater than basically 1, right? Z greater than y. So it will guide you for some range of omega. And z over y is equal 0.99. It will say, it can be implied that Z is lower than Y, right? So because in the right-hand side, you have an equation. So it can be further translated. It can be further translated by R squared is greater than 1 minus R squared plus 2 zeta R squared and similarly for this case, R squared is lower than 1 minus R squared plus 2 zeta R squared. So at first step, before reaching to this part, at first step, all you have to do is just go for these two cases and just take advantage of the equality and find the omega n for two cases. As soon as you obtain, just take and pick up those omega which are positive and correspondingly plug in here, and you will find some range. So if we do that here, I'll have only the last solution. So if we have a time, I can go over it and find it for you. So we have time, and I'll have only the final answer. In this case, when we solve the problem, I have a solution here. So I've given you the general way for tackling this kind of problem. You can now solve any problem. Just let me summarize, and because the solution manual is very, very concise and it is not written in detail. R max. Okay, if you remember in the several previous session, I told you that depending on we know this formula, right? This formula, there is a basically peak value Z over Y. We saw in the class that Z over Y is dependent on the value of R, omega and omega n, and also depending on the value of zeta. For each zeta, we have different graph. For each zeta, we have different graph, and for each zeta, there is a peak. For some of the zeta, there is a peak, and corresponding R that makes the graph peak we obtain. So here, for example, it is zeta 0. For other value of zeta, and for some zeta, there is no any peak, right? So the peak, there is a specific formula for finding the peak. You could take advantage of that in order to have some vision. So let me just, zeta is given 0.65. Zeta is 0.65, maybe become this kind of graph here. There's a peak basically. And the RA peak or RA max, there is a formula, 1 minus, which we already proved that, 1 over 1 minus 2 zeta squared, which if you plug in zeta, you will obtain as 2.54 or 59. Let me plot the graph approximately like this. When zeta is lower than 0.7, there is a maximum. Otherwise, there will be no any peak. So Z over Y versus R, frequency ratio omega over omega n. This is 1. So there is a peak and So for the seismometer, the more we are in the right region, the more our seismometer is exact, because as soon as this value z over y reach to the 1, there is an ideal case. Z is exactly equal to y. It will give you the correct answer. So ideal, practically we don't have this kind of seismometer, and there is some error basically. So if you solve the, so we already find by taking advantage of the formula R max. We have an idea that R max is obtained as 2. If you plug in R max, you have this data in the formula for z over y, you can easily identify this value. This value is z over y max is 1.012. Z over y max is 1, 2. So if you have basically this graph, you will never go and you will never waste your time, and you will not try this, because for this data, never z over y, z lower than y. So if you definitely, if you go for this, you will reach to R1 omega n1 negative and R2 negative. So you have to say it is not acceptable and it is not acceptable if you don't have the graph. And of course, this will give you the right answers. 1.1 equal to R squared 1 minus R squared plus 2 zeta R squared. If you plug in, basically, you have the omega n. Omega n is directly given to you. You have the zeta. If you plug in all the term, you will obtain 2 positive R. When the R is positive, you are in the right region. Your assumption is true. In the exam, you can blindly start from z over y is equal to 1.01. So if both of them are correct, you can say at the end, my assumption fortunately is correct. It is not necessary to go for 0.99. That's it, because R1 and R2 are positive. So 2.12, right? And R2 is 3.35. So you can go over the graph, and so 3.35, 2 point. So let me read the question. What is the lowest frequency that can be measured within 1% error? So what is the lowest frequency that can be measured? Mathematically point of view, I will come back to the graph. Mathematically point of view. So z over 1 is 1 point. If I want to solve this problem, I say like this, z over y. So I can imply that z greater than y by solving this equation. I'm pretty sure you will reach to this point. So R1 greater than, I'm pretty sure, 3.35, and R2 greater than 2.2. So so the commonality between the two will give you that the frequency should be greater than the frequency ratio, 3.35. So here, so the lowest frequency, basically this vibration pickup can measure is basically this value, 3.35. Because if we design this vibration pickup, if we basically stay here, we may increase the error like this here. So in order to make sure, definitely we will measure the input displacement within a 1% error. The lowest frequency that we could estimate is 3.35, right? So you have to say the lowest frequency is R over R is omega over omega n, therefore the lowest omega would be R omega n. Omega n is 4, R is 3 point. So you are not supposed to forget to find the omega, because R is frequency ratio. R multiplied omega n is given 4, which is basically 15 point. 15.9 okay, cycle per second. So F is, or Fn, the natural frequency is given in hertz. So 3.3 multiplied by 4 is 15.9 hertz. So the lowest frequency we could measure within 1% error is 15.9 hertz. So this is how you have to basically determine the range of frequency that either your seismometer vibration pickup or your accelerometer can measure. Similar scenario is there for accelerometer. You have to go for them. For the accelerometer, there is a similar formula. I hope I could deliver a correct answer, and hopefully you understand how to solve this kind of problem. If you have any question, just ask me.
Yes, I have a question. Would we
Yes.
lose point if in the exam, let's say we have this question and we just write that R is equal to 1 over 1 minus 2 zeta squared?
It is not necessary, just it is extra information I've given you. I just given in order to plot the correct graph. You are not supposed to plot. Basically, it was just simple information. But if you have the maximum amplitude, it will indirectly give you what we are located. And I'm pretty sure. So let me, because the zeta greater than 0.7 will have no any peak. Maybe in some cases, here, for example, is for zeta, for example, 0.8. So there is no any peak here. It is not necessary to, it will not necessarily help you 100%, but in some cases, it will give you some hint, but the general solution I have given to you will work for all the cases. So the seismometer basically has the seismometer Z/1 in the page figure 3. If you have the book, go and I don't have access to the book in this. So according to the value for the zeta greater than 0.7, there is no any peak basically, but for zeta lower than 0.7, there should be a peak. In some cases, maybe you are supposed to find zeta, maybe you are given the frequency ratio, so you have to go for 2 cases, and always it will help you to find the region. So try to take a look at, so if I find the, basically, so, okay. Okay. So if you have a book, go for basically page 77 in order to have a vision about the range of zeta, figure 0.11.2. And so I have given you a general solution, which will be work for 2 cases, accelerometer and seismometer, and you can find and the range of basically zeta and omega. So these are very important questions. The chapter 2.47. 2.47. 2.47. So let me read the problem. 2.47. A piston of mass is given 4.53 kilogram, is traveling in a tube with a velocity v is given. Velocity as 15.24 meter per second, and engages a spring damper as shown here. Determine the maximum displacement of the piston after engaging the spring damper. So maximum displacement after engaging the spring damper system. So how many seconds does it take? And after how many seconds we will reach to X max? So just let me know this problem is a forced vibration or is a free vibration, and give me your reason. So is it a free vibration or is a forced vibration problem? The mass is going to engage a spring damper system. So
I would say a free vibration.
Why?
Because it's chapter 2. Because there's no force.
Of course, just initial heat, right? Initial impact, yeah. Initial velocity, and there is no any permanent excitation. So this initial condition, and there is no any external force. In case of force vibration, of course, there could be initial condition, initial velocity, initial displacement, but here indirectly you could say there is no any initial, just impact and release. That's it. You could say it's a free vibration, and you have the response, and you have the general solution for the response. So for the free vibration, in the formula sheet, you have numerous formulas. So at first step, before starting solving the problem, you have to understand whether zeta is greater than 1 or zeta is greater, over damp case is critical damp or under damp. As soon as you calculate the range of zeta, you could go in the formula sheet and pick the correct formula. So in order to calculate zeta, we need to basically somehow, so if the zeta is given, so we have CK, we have everything basically. We could easily find the value of zeta. So at first step, you know that zeta is 2m omega n, right? M is given. Omega n you can easily calculate. Omega n is k over n. K is given, mass is given. Simply you could find omega n. 35, 4.53. Omega n simply 87.9 radian per second. So therefore C critical is 2m omega n. C critical therefore is 2.m is given 4.53 multiply omega n. Omega n is given 87.9. Therefore C critical is 796.37 Newton meter per second. As soon as you obtain C critical, you could easily and simply calculate zeta, C over C critical, because C is given, C critical is obtained, and you could go easily for obtaining zeta. C is given. In the problems 175, C critical we obtained recently. So zeta is nothing but 0. This is very important, my friend. Very, very important. This is your first part, first step. So you have to write this system, we are dealing, basically, we are facing with the oscillatory motion. Under damped case, you have to write oscillating or under damped case, oscillating motion, under damped. The response of the system would be something like this. Initial, you have to indirectly understand that initial displacement is zero. We have only initial velocity because there is an impact. Initial displacement is zero. So it will definitely start from zero. It reached to the max, and since there's a damping, the amplitude will be decay. So maximum amplitude, therefore, is the first time that the response reach it to the maximum. So basically, we are looking for x1, not basically for x2. Maximum amplitude, we are not looking for x3, x2, x1. And corresponding time that we will reach to this point. So if you have the response x of t, and you could easily take derivative and find the extremum, because at the extremum velocity and the slope is zero, right? The slope is zero at the extremum point, extremum, minimum, maximum. So you have the zeta, you will go for the formula sheet, or you could derive it by yourself. It's very simple. You could derive the response, or you could easily simply pick up the response from 2.616 x of t. Response of the system is basically e to the minus zeta omega and t multiplied by a cosine omega dt plus b sine omega dt. So this is a general solution, a transient solution for free vibration when there is a zeta between 0 and 1. From the information given to you, you have to understand basically that x of 0, these are very important. X of 0 is 0 because there's an impact, initial velocity, which is directly given to you. 15.24 meter per second. You have to just simply plug in. Displacement at time 0 is 0. So you have to put t0 in all terms and put the equation 0. So the first, by solving this, you will obtain a as 0. And therefore, if a is 0, therefore x of t response would be something like b e to the minus zeta omega n t multiplied by sine of damped natural frequency t. So x dot velocity at time 0 is 15. So you could easily take derivative from both sides. X dot of t is minus zeta. So there is a uv, right? U multiplied by v. So derivative of uv would be u prime v plus u v prime, right? V prime. So chain integration rule you can apply, and x dot of t simply minus b zeta omega n e to the minus omega n t u prime multiply by v. V is sine of omega dt plus u v prime. V prime is omega d cosine omega dt. So if you this is derivative, all you have to do is just plug in x dot t0 equal to 15.24. So if you put 0, this term would be 0 here. Therefore, you will reach B is x dot 0 over omega d. Initial velocity 15.24. Omega d is nothing but omega n multiplied by 1 minus zeta squared. (0.178) is initial velocity. So response, you have the general solution. X of t is b 0.178 multiplied by e to the minus omega n zeta omega n multiplied by t multiply sine of omega dt 85.75 t. We already find omega d. We could omega d is omega n omega n. We already obtained omega n at first step. 1 minus 2 to 0. Omega d would be 85. So it's lower than omega n. Omega n is 87. Omega d is 85. So we have this solution. We have the response of the system. We are basically want to maximum amplitude. All you have to do is just take derivative and equal to 0. It will mathematically, point of view, will give you the extremum point, maximum point, and the corresponding t would be t max. So if we have x, you have to just take derivative. So dx of t dt equal to 0. This will give you mean max point, extremum point. So derivative would be minus p zeta omega n e to the minus zeta omega n t dot sine of omega dt plus omega dp e to the minus zeta omega n t cosine omega dt equal to 0. So which t will make this equation 0? So you could simply divide both sides of this equation by b. You could divide both sides of the equation by e to the minus zeta. You can further simplify this equation by dividing both sides of this equation by cosine omega dt. B will be cancelled out. You can divide both sides of this equation by b. So let me cancel out b from both sides of this equation. This is multiplication dot, and b will be cancelled out. Of course, this term also is common. You could just divide it, the both sides of this equation, by this term. This will be cancelled out. Therefore, zeta omega n sine of omega dt is omega d cosine omega dt. Dividing both sides of this equation by cosine omega dt, therefore divide by you will have tangent of omega dt is omega d over zeta omega n. Therefore, you can further simplify it. Tangent of omega dt, we know that omega d is omega n s square root of 1 minus zeta s squared, zeta omega n. This term will be cancelled out. Therefore, tangent omega dt would be 1 minus zeta squared over zeta. So we have the zeta. If we plug in, then tangent of omega dt would be 1 minus 0.22 squared, 0.22 squared. Therefore, this is going to be 4.43. Simply, omega dt is tangent inverse of 4.43, which is going to be 1 minus 349, and simply t would be 1.349 over 8775 is 0.01.5. So this is a t. After this amount of time, we will reach to the maximum. Our first extremum point corresponds to the maximum. We know that if we plug in this t in the x dot t, make x dot t 0. So a slope is 0 at extremum point. Therefore, it is going to be related for this t. So this is correspond for this point. All you have to do in order to find x of t, x max, you have to plug in this time at the x of t equation. So simply x max, which is x at t is t max, which we obtained recently. It's going to be b 0.178 multiply e to the zeta omega n t, which we obtained now. Just plugging t in the Okay. Sine of omega n t. So X max is going to be finally 0.07 meter. So this is how you can basically find X max and T max analytically. And there is, of course, another simple solution, a rough estimation for the T for T max. Second method. So we are done with this question basically, but I'm trying to give you a hint. Second approach to tackle this question. Basically, X of T. So this is omega d. So I can say roughly this time T max is roughly approximately equal to omega d divided by 4. Why roughly? Because if we do that, omega d is sorry, tau d corresponding damp natural period. Tau d is this distance. So T is basically roughly would be tau d over 4 tau. So tau d is 2 pi over omega d, 2 pi over 85, 75 is going to be 0.0732. So T max is approximately tau d over 4, 0.0732 divided by 4 is going to be 0.0 meter. The rough value, this is the rough value, 0.18. This is the rough value, rough estimation. The exact solution, however, was obtained. Exact solution was 0. So this is a rough estimation. The rough estimation is strongly dependent on the value of zeta. So if you notice here, this is a little bit larger than real, basically, because of the value of zeta. For different zeta, basically, we have different graph. So the more the zeta, the more error we have. The lower zeta, the lower error between the rough estimation and the exact solution. So this is how you have to solve the free vibration. So simply, firstly, you have to calculate the zeta and determine the type of this problem: oscillating, over damp, critically damp, and find the appropriate solution. So if you have any question, you can ask. I hope you will solve all the problem in the exam, because they would be the same. It will not be very difficult. Just equation of motion, vibration isolation, logarithmic decrement. So we have effective damping, effective mass. We have solved several problems. Seismometer, accelerometer. These would be the typical question in the exam. So if you have any question, you can ask. Next session, yes.
That was very clear. Thank you.
You're welcome. Next session, we will go for chapter. We already started chapter 5. We solved 5.2, and next session we will go for chapter 5. So hopefully you can pass the exam with very good mark. And if you don't have any question, I'll see you in the next session on Wednesday.